Okay, well, let's have a look at this second handout here where the majority of these questions come from. So, centripetal force. Oh, and I need my favorite prop. The rubber stopper on a string prop. Been using this one for a few years. Okay, if you whirl a tin can on the end of a string, you find that you must keep pulling on the string. You pull inward on the string to keep the can revolving over your head in a circular path. I got a bad shoulder today, so I was like, I'm going to be able to do this. See here. Right? So as I'm spinning it in a circle, I have to apply a force to keep it going in that circle, right? This is being exaggerated thing, right? And you're going to be doing this tomorrow with a little sort of better device than just a string and a rubber stopper, although it's kind of close to the same. You will find tomorrow that some of you are much better at doing that than others. It's nothing about you, it's just that some people have an innate skill of being able to do it. I've been doing that for a while. A force of some kind is required for any kind of circular motion. Any force that causes an object to follow a circular path is called a centripetal force. And if you haven't highlighted that already on that second sheet that I gave you, you should do so. Because that is the definition of a centripetal force. Any force that causes an object to follow a circular path. Centripetal means center-seeking or towards the center. Oh, and I let away one of my big questions. Which usually I do this to start and say, which way is the force? This way. Yeah, that doesn't quite cut it, I'm afraid.
That's not what it's going towards you now.
Well, like when it's over here, which way is the force? Towards that wall, okay, and when it's over here, that way. Here, okay, and then, okay, so what would be a better way to describe than that way? Inward, towards the center, right? Quite often I get people to think that the force is actually outward. Is the force on the rubber stopper outward? The answer is no. Okay? Because you cannot push on a string along the stem string. Doesn't work. You have to pull on strings, right? So centripetal means center-seeking or toward the center. The force that holds the occupant safely in a rotating parallel right, as in figure 13.1, which I don't have here, is a center-directed force. Without it, the motion of the occupants would be along a straight line, they would not revolve. How many people have been to the fair and have rode that thing where you, what do they call it? You know, you stand up, they got that little chain. Hold on, hello, Mr. Reed, you're early.
The only copy?
Is that Harley?
Yeah.
No, I think I have another one.
Do you?
Yeah.
Because Mr. Jensen's not here, and I don't know where she put this stuff we're working on.
Is it called G-force? Something like that, right? You know what I mean, right? You go in, it's like a big circle cage, you got your own little spot, they got handles, and you put this rinky-dinky little chain over you that's for safety, right? And then it spins around like this, and then what does it end up doing? Like it sort of goes something like this, right? And are you perfectly vertical?
Yeah.
Pretty close, right? It's probably only 16, 17 degrees, really.
I heard someone puked on that ride and it came back in their face.
It very well could, right? I always laugh. I'm not going on that, by the way. I don't even like watching it, but I always laugh at that little chain. Like they might as well literally have a string like this, right? Because is that doing anything? No. What's holding you in place? Well, yeah. The force. Yeah. I mean, really, that's just there mainly so that you don't, like, when it's starting off going flat, that you don't step out of it. But once you start going up like this, it's inertia that's holding you in place. It's kind of neat, actually. It's a center-directed force. Without it, the motion of occupants would be along a straight line, and they would not revolve. Centripetal force is not a new kind of force, so don't think that, oh yeah, I got to learn this new force, right? It's simply the name given to any force that is directed at right angles to the path of a moving object and that tends to produce circular motion. And that should be highlighted as well, too. Okay? It's any force that is directed at right angles to the path. That's key. The force must be at a right angle to the path. As the rubber stopper goes whirling above your head, the force is, as Daniel pointed out, towards the center, but the rubber stopper is headed back towards him at the back of the room, right? 90 degrees. If I were to let go, where would it go? If I were to let go as it's spinning around and the rubber stopper is exactly in this position, traveling towards the back, towards Dallas's head, if I let go, it would continue into that straight line path, right? But because I apply a force, then I change the direction. So therefore, if there's a force, there must also be an acceleration. What kind of acceleration? Centripetal acceleration. The acceleration is also towards the center. Gravitational and electrical forces act across empty space as centripetal forces. Gravitational force directed toward the center of the Earth holds the moon in an almost circular orbit about the Earth. Electrons that revolve about the nucleus of the atom are held by an electrical force that is directed towards the center of the Earth. So the moon is traveling at great speed around the Earth, and there is a gravitational centripetal force holding it in orbit, pulling it back towards the Earth. Centripetal force plays the main role in the operation of a centrifuge. A familiar example is the spinning tub in an automatic washing machine that I'm sure many of you teenagers are unfamiliar with. Joke there. You may also have used it with a salad spinner. You know those kind of big, you pull the cord and it spins around, that kind of thing, right? They also use it in the lab to separate the different parts of the blood. That's called a centrifuge. In its spin cycle in the washing machine, the tub rotates at high speed. The tub's inner wall exerts a centripetal force on the wet clothes, which are forced into a circular path. The tub exerts great force on the clothes, but the holes in the tub prevent the tub from exerting the same force on the water. They cannot apply a force to the water because of the holes. The water therefore escapes. It's important to notice that a force acts on the clothes but not the water. Most people think that the force is outward, pushing the water away. That's not true. You're pushing the clothes away from the water. No force causes the water to fly out. The water will do that anyway as it tends to move by inertia in a straight line path, Newton's first law, unless acted upon by a centripetal or any other force. So interestingly enough, the clothes are forced away from the water, not the other way around. When an automobile rounds a corner, the sideways friction between the tires and the road provides a centripetal force that holds the car on a curved path. If the force of friction is not great enough, the car fails to make the curve and the tires slide sideways. The car will skid. And it's an interesting concept, and I challenge you the next time you're out driving, make a turn, and I want you to think about the road pushing you in that circular path. It's kind of a weird thought if you're making the turn. Don't run into it.
How are you going to tell us to skip that?
Yeah. Well, and we're going to talk about that. One of the assignments a little later is we're going to be dealing with cars rounding corners, whether they're dry corners, whether they're icy corners, whether they're bank corners or not, because you may have noticed that when your dad watches NASCAR, Jake, and I know he does, that the corners are bank. And that's not just to look cool, it's hold cars in line, hold in place. We're going to talk about that as well. So, centripetal and centrifugal forces. On the board, I've got the difference between the two, so that you need to know the difference between the two. In the preceding example, circular motion was described as caused by a center-directed force. Sometimes an outward force is attributed to a circular motion. This outward force is called centrifugal force. Centrifugal means center fleeing or away from the center. In the case of the whirling can or the stopper, it's a common misconception to state that a centrifugal force pulls outward on the can. Not true. If the can holding the whirling can breaks, it's commonly stated that a centrifugal force pulls the can from its circular path. But the fact is that when the string breaks, the can goes off on a tangent straight line path. Why? Because no force acts on it. Because Newton said an object in motion will stay in motion. But the part that everyone forgets about is the straight line path, constant velocity. Suppose you're the passenger member of a car that suddenly stops short. You pitch forward against the dashboard. When this happens, you don't say that something forced you forward. You know that you pitched forward because of the absence of a force which a seatbelt would have provided. Similarly, if you were in a car that rounds a sharp corner to the left, you tend to pitch outward to the right, not because of some outward or centrifugal force, but because there is no centripetal force holding you in circular motion as a seatbelt would provide. The idea that a centrifugal force bangs against the car door is a misconception. So when you swing a tin can in a circular path, there is no force pulling the can outward. Only the pull by the string acts on the can and pulls the can inward. The outward force, and this is key, outward force is on the string, not the can. I'll let that sink in for a minute. It is kind of weird. Okay? You, by virtue of the string, pull the rubber stopper in towards the center. That's the centrifugal force. That's tension. But the rubber stopper, because of inertia, is actually pulling on the string, that's the centripetal force, is on the string, not on the can. Now, just to make things a little more challenging, let's suppose there's a ladybug inside the whirling can. This can presses against the bug's feet and provides the centripetal force that holds it in a circular path. The ladybug in turn presses against the floor of the can, but neglecting gravity, the only force exerted on the ladybug is the force of the can on its feet. From our outside stationary frame of reference, we see that there is no centrifugal force exerted on the ladybug, just as there was no centrifugal force exerted on the person who lurched against the car door. The centrifugal force effect is attributed not to any real force, but actually to inertia, the tendency of the moving body to follow a straight line path. So the force, you could argue, doesn't exist because there's nothing causing it. It's inertia that's causing it. By telling that to the ladybug. Do they feel the force? Absolutely, they do, right? So here's the ladybug right here, right? And to an outside observer, outside the frame of reference, we see that force. Oh, do I have a next page here? Okay, now, caution. Brain explosion in the near future. Our view of nature is very much influenced by the frame of reference. Are these pages out of order?
Yeah.
Are they out of order here? No? I'm good? Our view of nature is very much influenced by the frame of reference in which we view it. When we sit on the seat of a fast-moving train, we have no speed at all relative to the train, but an appreciable speed relative to the reference frame of the stationary ground outside. We've just seen that in a non-rotating reference frame, the force that holds an object in circular motion is a centripetal force. For the ladybug, the bottom of the can exerts a force on its feet. No other force was acting on the ladybug. But nature seen from the reference frame of the rotating system is different. If you are inside the can with the ladybug itself, in the rotating frame, in addition to the force of the can on the ladybug's feet, there is a centrifugal force that is exerted on the ladybug. Centrifugal force in a rotating reference frame is a force in its own right, as real as the pull of gravity. So the force really only exists when the observer, person watching, is actually inside the rotating reference frame as well with the ladybug. Or if you were indeed the ladybug itself. Or if you're the person on the G-force, is that what it's called? People outside don't see that. People inside see the force. Hence, there's a fundamental difference. Gravitational force is an interaction between one mass and another. The gravity we experience is our interaction with the Earth. But centrifugal force in the rotating reference frame is not part of an interaction. It is like gravity, but with nothing pulling. Nothing produces it. It is the result of a rotation. For this reason, physicists rank it as a fictitious force and not a real force like gravity, electromagnetism, and the nuclear forces. Remember those four fundamental forces from grade 11? Probably not. Nevertheless, to observers who are in a rotating system, centrifugal force seems to be and is interpreted to be a very real force. Just as from the surface of the Earth we find gravity ever present, so within a rotating system, a centrifugal force is ever present. If you did go and see Interstellar with Matthew McConaughey and the rest of the gang there, you will remember that the spacecraft was doing what? Spinning. Why was it spinning like that? Big artificial gravity. Now it was a little bit, when I saw that spinning, I thought, okay, I gotta watch this a little more carefully here so I can talk about this in class. Because it was like, they started spinning and all of a sudden, oh yeah, they're sitting in their seat all like they're just walking around like they're in, a room kind of. It wouldn't quite be like that. It was a little bit fake, but because they're rotating like this, and it would depend on where in the spacecraft you are. Would you feel a different force on the outside when it's rotating like this? If you were out here, would you feel a different force than if you were somehow, I don't remember how the spaceship was made, but if you were, say, like here at the center, would you feel a different force? I think you all understand that, right? Did they ever, travel towards the center? I never really saw it in the movie. They sort of glossed over that, right? If you've ever been on a merry-go-round, you know for a fact that the further out you go, the what? The stronger the pull, right? If you're going towards the center, it's not quite as bad. Do you guys have this question? We don't have it as a clicker though, right? No. Okay. Okay. I know, brain explosion. Okay. A heavy iron ball is attached by a spring to a rotating platform as shown in the sketch, like a merry-go-round. Two observers, one in the rotating reference frame, that's the man right here, and one on the ground at rest, the woman over here, observe its motion. Which observer sees the ball being pulled outward, stretching the spring? Which one sees the spring pulling the ball in a circle? Do you have the answers at the bottom of your page? Yes, you do. Don't look at them. They're upside down. Think about that for a minute or so. I'm going to do attendance. Okay, so once again, let's just revisit this question. Two observers, one in the rotating reference frame, the man, and one on the ground at rest, observe its motion. Which observer sees the ball being pulled outward, stretching the spring? Which one sees the spring pulling the ball in a circle? Okay, first question. Which one sees the ball being pulled outward, stretching the spring? Man or woman? Man? Woman? Unsure. Okay, it's got to be one of those three, you guys. Unable to lift my arm. No one put their hand up. Good. You just leave it there, Mr. Reed's good. Oh, I've got the answer upside down. That's no good. It should be right there for me too, right? Which one sees the ball pulling the spring over? It's the man. The observer in the rotating reference frame. Sorry, the observer in the reference frame of the rotating platform states that centrifugal force pulls radially outward on the ball. In other words, the man, which stretches the spring. The observer in the rest frame, outside, that's the woman, states that the centrifugal force applied by the stretched spring pulled the ball into a circle along with the rotating platform. The rest frame observer can state in addition that the reaction to the centrifugal force is the ball pulling over the spring, but the rotating observer, interestingly enough, can state no reaction counterpart to the centrifugal force. So, like, he is unaware that he's rotating. Okay? The guy inside is, if it's a closed sort of system, right? Like, I mean, if there's a tree over here, right? He's going to see that he's rotating, right? But if this thing is enclosed with a wall, will he know that he's spinning? If he was born into that system and spent years growing up in it, would he even know that he was spinning? No, much like everyone in the room here today. Our Earth is spinning. Do you feel it? Do you see it? Well, I guess you could say if you look up and you see the sun, you see it rotating, right? But many people actually think the sun actually does what? They think the sun's moving, right? Us smart people know better. Don't look at the sun, by the way. Us smart people also know that too. Okay, so which one here? The man sees the ball being pulled outward, stretching the spring. That's the man. And which one sees the spring pulling the ball in a circle? That's the woman. Okay, part of your question. The spring in the sketch is observed to stretch 10 centimeters when the ball is midway between the rotational axis and the outer edge of the circular platform, i.e. this distance here is 10 centimeters. When you put the ball right in the middle. If the spring support is moved, the ball is directly over the edge. In other words, it now looks like this. So instead of the spring support being there, is it going to let me move this? Probably not. No. So instead of it being there, the spring support is here, and now the ball sits directly over the edge. Okay, so the support for the spring is not right in the center. If the spring support is moved so the ball is directly over the edge, will the spring be stretched more than, less than, or the same 10 centimeters? How many people say more than? How many people say less than? How many people are unsure? How many people are incapable of putting their arm in the air? I think it's more than 2. Let's check. The ball will have twice the linear speed. Why does it have twice the linear speed? Because it's going farther around the circle. Circumference has increased, right? In the same amount of time. So twice the distance, same amount of time. So it'll have twice the linear speed at twice the distance from the rotational axis. The greater the speed, the greater will be the centrifugal force, which will also be twice stretch the spring 20 centimeters. Hooks a lot. We'll see in chapter 18 that the stretch of the spring is directly proportionally applied to it. Yeah, that's hooks a lot. We're going to do a lab on that as well. Okay, so it actually stretches more than. It will actually stretch 20 centimeters. Heavy duty stuff, right? Don't worry, I'll tell you at the end exactly what you need to get out of this. Basically, what do you need to know? Between centrifugal, what's the number one thing you need to know? Yeah, but what's the number one difference that you need to know?
One
One is inward and one is outward. If you know that, that's you know, the basic understanding, right? Anything after that is sort of grading time. You must know that centripetal is towards the center. You must know that centrifugal is outward, and it only really exists when the observer is where?
In the rotating.
In the rotating reference frame. Those of us outside see it as inertia and reacting to that kind of thing. Okay, again, lots of talk. Hey, this is fun. Anyone got a helium balloon at home? How come when the car turns to the right like this, the helium balloon goes?
Because it's accelerating towards the inside of the curve.
Yeah, but how come everyone else in the car goes, well, everyone else in the car goes like that, so it feels like you're going to the outside.
But it because like the air gets there from like that side and then heal.
Exactly. Everything, literally everything in the car goes toward, let's say, to the outside of the car for sake of argument, because it's hard to say continues in a straight line because of inertia. Okay? So everything in the car goes to the outside, you know, everything will change. If there's something on your dash, you get your cell phone on the dash, which way the cell phone goes? Towards the outside, right? Including the air molecules in the car. So literally, I will draw a car right here. It's a very skinny one. Okay, here's the back of it. Okay, and there's the steering wheel. I'm looking inside, right? And if the car is going to go, yeah, it's terrible. The car is going to go like this, right? And all the air molecules go to this side, creating a region where it's more dense. And so the helium balloon is actually forced to the left because it's less dense. You can try that at home. If you do try it at home, take a video of it so we can see it. Okay? I can sort of demonstrate it if you want. Do I still have that device? Yes, I do. Okay, so here's the answers. You're spinning a bucket attached to a string in a circle above your head. What kind of force holds the stopper in a circular path? The correct answer would be A, centripetal. Very good. Many of you got that to begin with. In a washing machine during the spin cycle, the force is on the... What's the correct answer? We now know it's on the B close. Well done. A tube is placed upon a table and shaped into a three-quarter circle. A golf ball is pushed into the tube at one end at high speed. The ball rolls through the tube and exits at the opposite end. Describe the path of the golf ball as it exits the tube. Is it A, does it continue in the circle? Is it C, some sort of projected angle? Or is it B, straight line? Correct answer is B, my friends. Because an object in motion stays in motion, but the forgotten part is in a straight line at uniform speed. So it comes barreling out of there, right like that. Mr. Band is spinning a rubber stopper at a constant rate of 3 revolutions per second. The rubber stopper is accelerating. I'm guessing several people got this wrong, because the correct answer is true. Why is it true? Because the direction is changing. Right? The direction is constantly changing. So while the speed remains the same, the direction is changing. Therefore, there's an acceleration. What kind of acceleration? Centripetal acceleration. Acceleration towards the center. Mr. Van is still spinning the rubber stopper. What direction is the force in the stopper? Oh, well, I've sort of given this away, haven't I? Oh. In. The direction of the force is in, as is the acceleration. When you're driving your car and make a left turn, friction between your tires and the road causes the car to move to the left? That, my friends, is true. If there's no friction, what will you do? You will skid into a post. You may have experience with that, those of you that are winter drivers.